Hey everyone, welcome to another explainer. Today, we're taking something totally ordinary, engines, and pushing them to the literal absolute limits of physics. We're digging into a seriously fascinating paper from researchers over at the University of Maryland and Los Alamos National Lab. It's called Quantum Auto Engines at Relativistic Energies. So we're basically going to explore what happens when the microscopic world of quantum mechanics smashes headfirst into Einstein's special relativity. It's going to be a wild ride.
To kick things off, let's play with a really fun sci-fi concept. Could Star Trek's matter-antimatter engines actually exist? I mean, for decades now, science fiction has just teased us with this dream of harnessing the extreme, mind-bending laws of the universe to power our starships. We've all seen the warp drives lighting up the screen, right? But what if those concepts could actually be grounded in real theoretical physics? Could we actually build one?
Well, believe it or not, the authors of the paper we're looking at tackled this exact idea right out of the gate. In their introduction, they write, using relativistic phenomena as a source of power has long been a staple of popular culture, such as the matter-antimatter annihilation reactors that power the warp drives of Star Trek. I love that they just put it right out there. It perfectly sets the stage for us. What used to be pure science fiction is now getting a very serious look, using the cold, hard math of thermodynamics.
Okay, before we get completely lost in the relativistic quantum realm, because, trust me, it gets weird, let's ground this whole concept in something super familiar. When we talk about a quantum heat engine, honestly, you can just think of it as a microscopic car engine. Your everyday car parked outside probably runs on a standard, four-stroke auto engine. This paper is exploring that exact same thermodynamic cycle. But instead of a heavy metal cylinder and a tank of gas, it uses a single, solitary subatomic particle acting as the motor. Since the very beginning of thermodynamics, studying heat engines has been the ultimate key to figuring out how physical systems work. And now, researchers are scaling the whole shebang down to one single quantum particle. Incredible, right?
Okay, let's really dive into this. Let's map out the energy and frequency of an endo-reversible quantum auto cycle. This basically tracks the work and heat exchange of that single subatomic particle we just talked about. Now, instead of a physical piston moving up and down to change the volume of a cylinder, in the quantum world, we're actually changing the frequency of the trap that's holding our particle. So picture energy on the vertical axis and frequency on the horizontal. It's this incredibly elegant way of visualizing how a microscopic motor breathes in heat and breathes out physical work.
Let's walk through the 4 steps of this quantum auto cycle. And remember, this perfectly mirrors the car engine. First up is isentropic compression. This is where we increase the frequency of the oscillator to squeeze or isolate the particle, which is exactly like a piston compressing that fuel-air mixture. Next, we hit isochoric heating. Here, our little particle absorbs heat from a hot bath. Think of this as the spark plug firing and igniting the gas. Then comes isentropic expansion, the power stroke. This is where the expanding system does actual physical work. And finally, step 4, isochoric cooling. This is the exhaust stroke, where the system releases the leftover heat into a cold bath. It's literally the exact same process you use to drive down to the grocery store, just scaled down to the ultimate microscopic level.
Now, here's the real narrative twist. What if we force our tiny quantum car engine to operate under the absolutely extreme rules of special relativity? I'm talking about moving near the speed of light. To figure out how that would even work, physicists use something called a Dirac oscillator. Basically, this is a relativistic extension of the standard quantum harmonic oscillator. It was originally derived to describe particles moving so incredibly fast that classical quantum physics just flat out breaks down. The moment you introduce the speed of light into these equations, the rulebook gets thrown right out the window.
So, what exactly gets so weird when we go relativistic? Well, in relativistic quantum mechanics, you don't just have your normal run-of-the-mill particles. You actually get an entire bonus pool of energy from antiparticles. We can visualize this with positive particle states up top and negative antiparticle states down below. And here's the kicker. Because of a funky mathematical property known as the stability of the Dirac sea, these positive and negative states absolutely do not mix. So the engine is actually operating as a mixture of 2 separate ideal gases, one made of particles and the other of antiparticles. This dual nature completely, and I mean completely, overhauls the thermodynamic math of our little engine.
And that brings us to the central paradox of the whole paper. When the researchers calculated the performance of this relativistic engine and compared it head-to-head with a standard, non-relativistic quantum engine, they found something totally counterintuitive. The relativistic engine actually outputs more raw physical work and power. It essentially just has more muscle. But, paradoxically, it operates at a significantly lower efficiency than the standard engine. Seriously, you have to ask yourself, how in the world can an engine produce more work but be less efficient?
And this brilliantly illustrates the why behind that extra power. The thermal momentum distribution explains exactly why the relativistic engine packs such a bigger punch. If you picture a sharp, narrow spike, that's your standard Maxwell-Boltzmann distribution for normal, non-relativistic particles. But then, if you look at the broader curve, the Maxwell-Jüttner distribution for relativistic particles, you see something different. Because that curve is so much wider, it means relativistic particles have a way higher probability of possessing super large momentum. And since work is extracted through changes in momentum, boom, this directly results in our engine extracting more physical work.
But wait, we still have that paradox to resolve. If it produces more work, why is the efficiency so much lower? Well, the catch lies in the fundamental limits of space-time itself. The speed of light rigidly restricts the allowed dynamics of our particle, a concept physicists like to call the light cone. Because the Dirac oscillator potential has a linear frequency scaling, rather than a quadratic one, the relativistic engine effectively acts like a car cylinder with a significantly reduced volume. So it pulls more heat from the hot bath to get that extra work. But because of this constrained, effectively smaller volume, the ratio of work extracted to heat absorbed, which is literally the definition of efficiency, actually drops.
So the absolute crucial point here is that despite all these massive differences in work extraction and efficiency, the researchers found that both engines reach exactly one common mathematical milestone, just one. When you tune both the non-relativistic and the relativistic engines to output their absolute maximum power, their efficiency at that specific point perfectly matches the classical Curzon-Ahlborn efficiency. I mean, this is a huge finding. It proves that whether you're building a standard microscopic motor or a crazy relativistic engine driven by particles and antiparticles, the fundamental thermodynamic limits at maximum power remain beautifully, perfectly universal.
Now you might be sitting there thinking, okay, this is some truly fascinating theory, but come on, can we actually build it? And the answer is yes, absolutely. Scientists are proposing 3 specific methods to test this on a lab bench right now. First, they can use trapped ions, utilizing lasers to simulate Dirac dynamics. Second, they can use Dirac materials like graphene chips where charge carriers actually behave like relativistic massless particles. Or third, they could even utilize microwave resonators built from dimeric chains of disks. We aren't just theorizing on chalkboards anymore. We are literally engineering relativistic thermodynamics.
Which leaves us with a truly provocative question to end on. Think about this. If we can use things like graphene and trapped ions to simulate the extreme environments of the cosmos, will studying the thermodynamics of black holes and cosmic jets at the lab bench ultimately power our future? Understanding these relativistic quantum engines isn't just about unraveling the mysteries of the stars anymore. It's about laying the literal groundwork for the most advanced technologies imaginable, right here on Earth. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.